This is a video from section 16.4 found in a Calculus 3 class. Use Green's theorem to evaluate the line integral along the positively oriented curve. Keyword or key phrase being positively oriented. Number 5, we're going to look at the integral over c of y e to the x dx plus 2e to the x dy. C is the rectangle with vertices 0, 0, 3, 0, 3, 4, and 0, 4. And I draw a picture of a rectangle. Notice the arrows going in the counterclockwise direction. That's what I mean by positively oriented. So in other words, I'm going to go from 0, 0 to 3, 0 to 3, 4, back over to 0, 4, back down to 0, 0. Now notice how this line integral is of the form the integral over c of m of xy dx plus n of xy dy. Okay, so you can see where I'm going to get my functions m and n, and that's going to be the case for all of these questions. Now, m of xy is y e to the x, n of xy is 2e to the x. The partial of m with respect to y is e to the x, right? Because x is constant, right? And the derivative of y with respect to y is 1. N of xy is 2e to the x. Again, the partial of n with respect to x is 2e to the x. So the integral over c of y e to the x dx plus 2e to the x dy is the double integral where the x limits go from 0 to 3. So notice how x goes from 0 out to 3, literally. And then y goes from 0 up to 4. And so that's what the y limits are. Now, you're going to integrate the partial of n with respect to x minus the partial of n with respect to y. That's my integrand. So remember that 2e to the x minus e to the x is e to the x. So we're going to do the innermost integral first. So in other words, I'm going to integrate from 0 to 3 of e to the x dx. I'm going to take that result and then integrate from 0 to 4, again, of that result, dy. Okay, so start inside, work your way outside. So this is the integral from 0 to 4 of e to the x evaluated from x equals 0 to x equals 3 dy. Okay, now why do I say x equals 0 to x equals 3? Because sometimes you're going to find that that integrand will have more than one variable involved, and it's really much better to keep track of your limits. So in other words, what you're plugging in for which variable, right? And so using the fundamental theorem, I'm going to integrate from 0 to 4 of e to the third, right, replace x with 3, minus e to the 0, replace x with 0, dy. But this is e to the third minus 1, that quantity times y evaluated from 0 to 4, replace 4 with y, and I get 4 times e to the third minus 1, and then remember, e to the 0 is 1. Okay, so that's my final answer for problem number 5. If we take a look at problem 7, we're going to get the integral over c of x squared y squared dx plus y times arctangent of y dy. C is the triangle with vertices 0, 0, 1, 0, and 1, 3. So you notice I draw a picture of a triangle. And there's a really, really nice technique in order to find my limits for x and y. Now, so what I do is I draw an arrow and I go, oh, I notice that I hit the y-axis, or excuse me, the x-axis first, right? So I enter y equals 0. And then I go, I leave the line through the points 0, 0, and 1, 3. So I enter the x-axis, I leave y equals 3x, because that's the equation of the line through the points 0, 0, and 1, 3. It's a really, really slick technique to try to find those innermost limits, because you're along a line, And so when x changes, y changes. So if you compare the last example, you notice if I enter in, I can enter y equals 0, I leave this horizontal line. It's a constant line. So the y value never changes. But when you're over here, this y value changes. So notice when x is a half, for example, y is 3/2. But when x is a third, y is 1. And so the y value is changing. And so that's why we have to have y equals 3x here. And then x is going to go from 0 to 1. So we want a constant value on the outer limits. That's how I come up with my limits of integration. And this is exactly the way I teach it in chapter 15. Now, m of xy is x squared y squared. N of xy is y squared times arctangent of y. The partial of m with respect to y is 2x squared y. The partial of n with respect to x is 0. Remember, y is constant. So the integral over c of x squared dx plus y squared arctangent of y dy is the double integral where the y limits again go from 0. I enter through the x-axis. I leave through the line. So I go from 0 to 3x along an axis parallel to the y-axis, so to speak, right? And then my x limits go from 0 to 1. My integrand is the partial of n with respect to x, that's 0, minus the partial of m with respect to y, that's 2x squared y. So when I go to integrate, I'm going to integrate from 0 to 1 of negative x squared y squared evaluated from y equals 0 to y equals 3x dx. So I'm going to replace y with 3x and then replace y with 0 and subtract those results essentially. And so you can see I'll pull the negative out in front and I'm going to integrate from 0 to 1 of x squared times 3x quantity squared dx. But that simplifies to negative the integral from 0 to 1 of 9x to the 4th dx. And again, remember, I'm going to subtract 0, so I didn't put that in. So I hope that's okay. So again, I'm going to integrate negative the integral from 0 to 1 of 9x to the 4th dx. That's negative of 9/5 x to the 5th evaluated from 0 to 1. And so the answer to number 7 is negative 9/5. Number 9. Suppose we have the integral over c of y plus e to the root x dx. Don't let the e to the root x bother you, right? That could have been e to the square root of x plus arc sine of x. Because remember, we're taking the partial with respect to y of this function here. Okay? So again, we have the integral over c of y plus e to the root x dx plus 2x plus cosine of y squared, that quantity dy. C is the boundary of the region enclosed by the parabolas y equals x squared and x equals y squared. And so we have two parabolas. Now I want you to notice something. I'm going to enter through this parabola in black, right? The parabola in black is y equals x squared. I'm leaving x equals y squared, but we have to solve for y, right? Because these are y limits. So when I solve for y, I get y equals square root of x. Now you might ask, why isn't it y equals negative square root of x? And the reason why is because we're not on the bottom half of the parabola. We're on the top half. And the top half is non-negative. So we're going to leave y equals square root of x. So we can't forget to take this equation and solve for y in terms of x because they're y limits. And so notice how these arrows run parallel to the y-axis. That's how I know they're y limits. if those arrows ran parallel to the x-axis, they would have been x limits. So this is how I'm getting my innermost limits, okay? And that's what I have, you'll see in a minute. That's what I end up getting. Now, m of xy is y plus e to the root x, so the partial of m with respect to y is 1. And then n of xy is 2x plus cosine of y squared. Partial of n with respect to x is 2. So if I take this line integral here, I'm going to write it as a double integral where the outer limits are from 0 to 1 with respect to x. My inner limits are from x squared to square root of x, right? Of 2 minus 1, so that's 2 is the partial of n with respect to x. And then I'm going to subtract the partial of m with respect to y. That's my 1. So that's how I'm getting my integrand. So it's the integrand is the partial of n with respect to x minus the partial of m with respect to y. This is how I come up with my integrand. Okay. Now, this is the integral from 0 to 1 of y evaluated from y equals x squared to y equals square root of x dx. So this is the integral from 0 to 1 of square root of x minus x squared dx. And straight out of Calc 1. So this is 2/3 x to the 3 halves minus 1/3 x to the 3rd evaluated from 0 to 1. Pop the 1 in for x, and we get 2/3 minus 1/3. I don't have to worry about 0. And so the correct answer for number, I believe this is 9, would be 1/3. Number 11. Suppose I have the integral over c of y cubed dx minus x cubed dy. Now, by the way, I would perhaps recommend writing this as the integral over c of y cubed dx plus negative x cubed dy. It might help you identify your functions m and n easier. So it's got to be a sum for this to make sense. Now, c is the circle x squared plus y squared equals 4. That's a circle centered at the origin of radius 2. Okay? And we're going to integrate over everything inside the circle, as you're going to see in a minute. Now, m of xy is y cubed. N of xy is negative x cubed. Common mistake is people might forget that negative, and it needs to be there to apply that Green's theorem. Now, the partial of m with respect to y is 3y squared. The partial of n with respect to x is negative 3x squared. And it's very tempting to want to do polar right off the bat. I would recommend waiting a minute, okay? So if I take the integral over c of y cubed dx minus x cubed dy, that's the integral, that's the double integral over x squared plus y squared is less than or equal to 4. So I'm integrating over everything inside the circle here. Okay, everything. And my integrand is the partial of n with respect to x, partial of n with respect to x minus the partial of m with respect to y dA. Okay, with respect to area, basically. Now, pull out that negative 3, and this is the double integral over x squared plus y squared less than or equal to 4 of negative 3 times x squared plus y squared dA. I don't convert to polar right away. Now, from here, I am going to convert to polar because it just makes sense. We're integrating over this circular region in everything inside that circular region, right? Now, over here, I'm going to pull the negative 3 out. My limits are from 0 to 2 pi on the outside, right? My theta limits. My r limits go from 0 to 2. X squared plus y squared is equal to r squared, right? That's how we go to polar. Now, remember, dA is r dr d theta. If somebody needs to derive r, I could do that in another video. But there is a reason why that r is there. Think of the pirate, r, dr, d theta. Cheesy, but if it works, why not, right? Now, r squared times r is r cubed, and the integral of r cubed dr is 1/4 r to the 4th. So we have -3 times the integral from 0 to 2 pi of 1/4 r to the 4th from r equals 0 to r equal 2 d theta. But if I plug 2 in for r, I get -3 times the integral from 0 to 2 pi of 4 d theta. So this is -3 times 4 theta from 0 to 2 pi. And the answer to number 11 is going to be -24 pi. And that'll do it for this video. This is section 16.4. We worked problems 5, 7, 9, and 11 in a Calculus 3 class, and problems came out of Stewart, 9th edition. Thank you.